So we're now going to briefly review some of the properties of discrete time Fourier series. Since most of these properties are very similar to those of the continuous time case that we've already talked about, so I am not going to give a proof for most of them. I'm just going to quickly review them very quickly. First off, so if x of n is periodic, it has Fourier series coefficient a sub k is y of n is another periodic signal which has Fourier series coefficients b sub k, and one of course the assumption is both of them have the same period. Then linearity is pretty straightforward. The Fourier series coefficients of this sum just ensures that the in the Fourier domain the Fourier series coefficients are also the superposition. So capital A times a sub k plus capital B times B sub k, which is exactly the same as we had in the continuous time case. For the frequency shifting, x of n minus n naught, very once again similar. So you just what that affects, what that results in the Fourier domain is just a multiplication of the Fourier series coefficients of x by this simple exponential. Once again, very similar. Conjugation is exactly the same. X conjugate of n results in a Fourier series coefficient of a conjugate minus k. Time reversal in the time domain just flips the Fourier series coefficients as well. And once again, very similarly to the continuous time case, all of those conjugation symmetry properties also hold. If x of n is real, then the Fourier series coefficients are conjugate symmetric. If x of n is real and even, the Fourier series coefficients are always real. If x of n is real and or the AKs are Fourier series coefficients are purely imaginary. First difference is something which is slightly different, but pretty straightforward. So first difference is analogous to the first derivative in the continuous time case, which is just simply the difference between the signal at current time and the signal just immediately in the past. And if this is the signal, which is x of n minus 1, which is the first difference, the Fourier series coefficient of this first difference is just given by this, which can be easily derived from the time shifting and the linearity properties. Multiplication property is something which is slightly different. So as you recall, in the continuous time case, if two periodic signals are multiplied with the same period, the Fourier series coefficients are convolved. That's what we had in the continuous time case. You have something similar here. The only difference being that the summation here is over a finite set of indices. So it says L is being summed over any interval of length n. For example, this could be from 0 to n minus 1. It could be from 1 to capital N. So any interval that you pick of length capital N, this is what this notation denotes. So this is, of course, different than discrete time convolution. I am not going to do a proof for this. I'll leave this off as an exercise. But just for your information, this convolution is basically called periodic, or sometimes it's also called circular convolution. And I will not go into a lot of details about this. And then finally, Parsev's relationship is more or less the same as in the continuous time case as well. So the average power in the discrete time periodic signal can be obtained as simply the summation of the Fourier series coefficients. The difference, of course, are this absolute sum squared and then sum over all the Fourier series coefficients. But the difference, of course, is that you're not summing from minus infinity to plus infinity, but rather over a finite interval of length capital N. The proof for this, once again, I'm leaving this off as an exercise. I think it's one of the end of chapter problems anyway. One property that I am going to prove is this frequency shifting property, which is stated here, which is if I multiply the discrete time periodic signal with this exponential, which is e raised by j capital M, where capital M is some integer, then what results in the Fourier domain is just that the Fourier series coefficients are shifted by this integer capital M. The proof for this is straightforward, but let me do this nevertheless. So let's just quickly try to do a proof. I would encourage you to pause this video now and try the proof on your own, and then unpause it. So hopefully you're doing that right now. So let me give you the answer nevertheless. So let's say the Fourier series coefficients of this signal are bk's, and we're required to find bk. So bk's by the analysis equation is just simply equal to 1 upon n. Remember, the period of this signal, which is product of this times this, is once again capital N, because the period for this is capital N, the period for this is also capital N, and therefore the period of the product stays capital N. So this is the 1 upon n is a period, and then I sum over any interval of length n, which is capital N is a period, and then this is a signal I'm interested in finding the Fourier series coefficients of. So this is x of n. So this is a signal I'm interested in finding the Fourier series coefficients of, times, of course, minus j k 2 pi by capital N times n. And just a simple manipulation here would directly yield the answer. So this is, let me bring x of n outside, and this is e raised to power minus j k minus m 2 pi by capital N times n. And clearly one can see that this is very, very similar to the Fourier series coefficients of the original signal, the periodic signal, except that instead of k, you have k minus m, k minus capital M. So therefore, this really is a k minus m, and that just completes the proof. And this, the reason why it's called the frequency shifting property, is because multiplication by this exponential here results in a shifting of the spectral coefficients, which is a shifting in the Fourier domain on the frequency domain. So if you want to shift some frequencies in the Fourier domain, this is what you need to do, is to multiply the period, multiply the time domain signal with this exponential. This is something we're going to talk about later in the Fourier transform as well.